Hello, this is section 6.3, page 342, word problems. So let's go over these, and hopefully watching the video will help you with these practice questions. And pay attention to not only what I'm writing, but pay attention to the words I'm using. Okay. So the surface area of a cylinder is given by the polynomial. The cylinder has a radius of 2 centimeters, and a height of 5 centimeters. Find the surface area of the cylinder. Use 3.14 for pi. So first thing I want to do is identify some key words: radius and height. Now you'll notice that the radius, letter R, and height, letter H, found in this polynomial. So what you need to do automatically is to convert the radius into an expression that says R equals 2. And also the height is equal to 5. So you're writing what you read into what we call algebraic expressions. The following step here is to rewrite the given surface area as an equation with the polynomial on the right side. So here's what I have. I have the surface area of the cylinder is equal to 2 pi r squared plus 2 pi RH. Again, we will derive this formula later in the year, but now we are just using it. And then a final note I want to make is that sometimes drawing out a picture is very helpful. So if I were to draw a cylinder, not perfect, but it doesn't have to be. That would be a radius, and that would be the height. And so what we're looking for is the amount of surface area this can has. And it looks like a soda pop can. So we've got 2 circles, and then the surface area around the object, okay? So, with that said, let's substitute and find that surface area. 2 pi times 2 squared plus 2 pi times 2 times 5. You notice that I leave pi alone? You can multiply in any order you want. It's the commutative property, so 2 squared is 4 times 2 is 8. Remember that. 2 squared is 4 times 2 is 8. Okay, 8 pi, one step at a time. 2 times 5 is 10, plus 2 is 20, or times 2 is 20. And then combine your like pi terms, which is 28 pi. This is the exact answer in square centimeters, but if we use 3.14 as our approximation, what we end up getting is 28 times 3.14, and that is 87.92 square centimeters. Okay, moving on. Next question is involving how long it takes to brake given a travel speed, which we call velocity. So in the United Kingdom, the authorities use a polynomial 1/20th v squared plus v. V is the velocity or miles per hour that you travel, for calculating the number of feet needed to stop on dry pavement. In the United States, many use the formula 96,000 v squared. Both formulas are based on speed, v, in miles per hour. Calculate the stopping distance for a car traveling 45 miles per hour in both the UK and the US. So this 45 miles per hour, that's what we call v, velocity or speed. And so let's write that down. The velocity of the object is 45 miles per hour. Now, in order to find the stopping distance, what I will write is the UK stopping distance formula is equal to 1/20 times v squared plus v, where 45 is v. So let's substitute. And that's not an R. These are V's. Now working this out mathematically. So 45 squared divided by 20 is 101.25. Add 45 to that, and we end up with 146.25. Now this is the amount of feet that is required to stop if you're traveling 45 miles an hour in the UK. Now for the United States, we have here is this formula. So substituting 45 miles an hour, using our calculator to compute this, so that's 45 squared times 96 thousandths, and it's 194.4. Now we discussed this in class the other day. I had said that I think that the differences in formula come from the fact that in the UK it's a smaller country, it's smaller cars, and so they could stop quicker. And so this formula was derived using smaller car data. And so we're thinking that smaller cars stop sooner, given the speed of 45 miles an hour. Where in the United States, you have bigger cars, bigger trucks, larger vehicles, and so traveling at 45 miles an hour might take longer, and so that's why this formula is different and gives us a longer stopping distance. So sounds like it makes sense, possibility. Next question. Okay, this question's a little more elaborate, so let's read it. It says that the height of a rocket in meters t seconds after it is launched is given by the polynomial, where a is always negative 9.8, v is the initial velocity, h is the initial height. Use the information and select the best answer. So we're looking at this rocket called the 300X. Okay, it was launched at a height of 10 meters, and what was its height after 3 seconds? Alrighty, so let's look at this. Let's try to analyze the information we're getting. So we've got to use this formula, okay? It's going to give us the height. So I'm going to write the height of this rocket, and this is a special type of notation. It's called function notation. The height of the rocket in time, which is the height of t seconds, the height of the rocket in t seconds, is equal to this formula. This is a physics formula, and there it is. So we've got some variables called a, v, t, and h. So let's see if we're going to find those values in the variable. So we're given that a is always what? Negative 9.8. And that's the acceleration of velocity. So I'm going to write that down. So a, write it over here. And then we're also given that the height, well, no, let's look at the v, velocity. We're given the velocity here, right? So, I don't want to confuse you, but there's v, velocity, and we know that's here. Look closely, 250. And then we're also given that the h is the initial height, so we'll call that h, and it says that we're launching the rocket at a height of 10 meters. And then finally it says, what is the height after 3 seconds? Okay, so the letter t represents second, stands for time, and we know that's going to be 3. And it says, what's the height? Well, we can find that. H of t is the height, where h is the starting height, so it's a different value, right? So the final height would be Substituting for AT, velocity is 250. 3 seconds. Oh. And what I'm going to do before I continue to write, I've got to slide this over, just running out of room. So let me just take this and move it over. Give myself some room. Three seconds, see it? And the height was 10. So just so that we're not too confused, I'm going to color code this. The acceleration A is 9.8 meters per second squared. It's this number here. The velocity is 250. This number here. See it? The height is here. And then the last value here is the time in seconds, which is here. So let's clean this up. Okay? So half of negative 9.8, right? Negative 9.8, when you divide that by 2, essentially, it's 4.9. So negative 4.9. And 3 squared is 9. Now 250 times 3 is 750. Plus 10 is 760. So here, let's go 760, and we're going to subtract whatever that value is. 9 times 4.9. So not too bad arithmetic here. It's not that difficult. You can do this all by hand and get a solution. So what I'm getting is 715.9 meters. Now, I may have been saying feet this whole time. That was a mistake. But that is the height that the rocket has traveled. All right? Good job. All right, last question. Same situation, just it's number 7. And so we still have the same issue, same formula. But now we have a rocket, 2 rockets, the 4400i and the Q99. And we want to answer the question that says, after how many seconds were the rockets at the same height? So that is a question where you're solving 2 equations simultaneously, and you might remember that from Module 1. So let's set this up. Okay, so we've got this rocket here, the 4400i. I'll write some information down. It says it was launched from the ground, so we know that the initial height is 0. Okay, and we also know that based on the chart here, that the 4400 has a velocity of 125, the initial velocity, so B is 125. And both have an acceleration due to gravity of negative 9.8. And the question that we're trying to find is when do the rockets have the same height after so many seconds? Okay? And so we're trying to evaluate when they have the same height after t seconds. And so we don't know the seconds there. So that's for that situation. Now the other rocket, the Q99, alrighty, the Q99, similar situation. The Q99 was launched from 135 meters above the ground. So the initial height there was 175. The velocity based on the chart is 90 meters per second squared. And acceleration is the same. It's gravity. Again, we're trying to find the time when these 2 rockets had the same height. So let's substitute these values into this one equation. So I have 2 separate rockets using the same equation. So we're going to have 2 equations, and we're going to set those equal to each other and solve for t, time. So let's do it. So the 400 is going to be on the left side, and the Q99 will be on the right side. So the 400 will be Okay? And then the other rocket will be on this side here. And we're setting them equal to each other since we are saying that the heights have to be equal. Remember, this formula gives you the height. And so we're saying that the height of the 4400i is going to equal the height of the Q99, which is this expression. Velocity is 90. Starting height is 175. And so we've got the height on the left and right side, and they must equal each other. So let's solve for t and find out what time in seconds do the heights equal each other. So computing this here, we know that that's negative 4.9 t squared plus 125 t. 0 means nothing. Negative 4.9 t squared plus 90t plus 175. Well, we get this side here, it cancels with that side there, since they're opposites. And if we subtract 90 from each side, we end up with, let's see, that's 10, that's 35. Equals 175, and if you divide by 35, if I'm not mistaken, I think we get 5 seconds. Yep. Yeah, let's double check it. 175 divided by 35 is 5. Yeah, so it's 5 seconds. So these rockets have the same height at 5 seconds. And that's the show. We'll talk more about this lesson if need be. Study hard and learn a lot. Bye-bye.